Hello, very good morning to all of you. So today we are going to continue on with the chapter 5 group 2, where in this video we are going to have a look at two very important things that you need to know on how to explain. The first is about the thermal stability of the group 2 carbonate nitrate hydroxide. And then we are going to have a look at the solubility of the group 2 sulfates here, right? So without further ado, let's begin. So let's start off with the thermal stability of group 2 carbonate, nitrate, and hydroxide. So here are the formulas of the carbonates, right? So you have BeCO3, MgCO3, CaCO3, SrCO3, and BaCO3. And these are the formula for the nitrates. So you have general formula of MnO3 okay, and then finally you have the formula for the hydroxide, where you have the general formula of NOH2. So no matter what, no matter that we are discussing carbonate, hydrates, or hydroxides, so all of them share the same trends. So what is the trend of the thermal stability when going down to the group 2 compounds? So we say that stability of the group 2 carbonate, nitrate, or hydroxide increase going down group 2. So then you need to know how to write the balanced chemical equations for the reactions. If you are now discussing about nitrates, so you have two MnO3, please put an arrow and under it put a triangle sign for a sign of heating. So you form 2MO plus O2 plus 4NO2 gas. If it is carbonate, MCO3 under heating, you form MO plus CO2. And with this hydroxide, MOH2, when you heat it, you form MO plus H2O plus H2O in here. All right. So how are we going to explain the trend of thermal stability? We start off with the primary factor, which is the cationic radius increase down group 2. Okay. So as the cationic radius increase down group 2, the charge density of the cation decrease. Okay, charge density of the cation decrease. So normally in this case, we will usually advise students, if you want to write a good structure or essay, we always advise students to use a smaller ions to explain. Okay, so if you, let's say in this case, you use beryllium to explain, all right? So here are the few very important points in here, okay? So what happens when you have a high charge density? So like in this case, as I mentioned, you use beryllium as examples. When you put close to a large carbonate ions, so what will happen? So due to the small cations in here, it is able to attract the electron cloud of the carbonate ion close to it. Okay, so as a result, so if you look carefully, the oxygen, which is the closest to the beryllium, so at the same time you attract the oxygen close to it. So what will happen? The high charge density that has a high polarization power of the beryllium is able to distort the electron cloud close to it, hence weakening the bonds. Let's say a carbonate, if it is CO bonds, making them easier to be broken. So as a result, so you form beryllium oxide plus carbon dioxide here, right? So in terms of the sentences or in terms of paragraph, how are you going to explain that? Okay, let's continue on. Okay, so we are going to mention that beryllium has a small ionic radius than barium, let's say. Therefore, it has small size and high charge density of beryllium, cause beryllium ions to have a high charge density. So as a result, beryllium ion has higher polarizing power. So this will allow the beryllium ion to polarize the large carbonate ions or nitrate or hydroxide, cause the oxygen in the carbonate or nitrate or hydroxide to attract closer to the beryllium, therefore weakening the CO bond or rendering the CO bonds in carbonate. So if it is nitrate, then we say NO bond. If it is hydroxide, then we say OH bond, hence decomposed. Okay, so furthermore, beryllium oxide is more stable than the beryllium carbonate, which makes the reaction occur more easily at a lower temperature. Okay, so this is how we are going to describe the thermal stability of the group 2 carbonate, nitrate, or hydroxide. So the points are all the same in here. Okay. All right, so this is for the thermal stability of the cation from the sense of the anions in here. Okay, so we are going to compare, let's say, for calcium. So these are the decomposition temperature for the calcium hydroxide, calcium nitrate, and calcium carbonate. So as you can see in here, the decomposition temperature increased from nitrate to hydroxide to carbonate. So how are we going to explain this phenomenon? Okay, so, of course, when we talk about decomposition, you have to write the dissociation equations, okay? So, for the relative thermal stability of the group 2 anion, it depends on two factors, which is the charge and also ionic radius. So, higher the charge of the anion, so stronger the attraction forces between the cation and anion, okay? So, while the smaller ionic radius of the anion, it makes it closer between the two nuclei of the ion, therefore greater the attraction forces. So in this case, if you relate with what we have discussed so far, so carbonate ion has the highest charge here. So when you have a highest charge, therefore CaCO3 has the highest thermal stability among the three compounds in here. Whereas for OH minus and NO3 minus, they share the same charges. However, OH minus is smaller than that of the nitrate ions. Therefore, the ionic bonds inside them is the strongest, making the thermal stability of the calcium hydroxide is greater than that of the calcium nitrates. All right. So this is how we are going to describe the group 2 thermal stability for the anions part here. Okay. Right. We are going to continue on with the lattice energy. So what is actually a lattice energy? So you have to define all of them. Lattice energy is the energy released when one mole of solid crystal lattice is formed from oppositely charged gaseous ions under standard conditions. Okay, so you have to know how to write the thermochemical equation. So if you have Na plus Cl minus give NaCl solid, Mg2 plus gas plus O2 minus gas give MgO solid. Ca2 plus gas plus 2Cl minus gas gives CaCl2 solid. So if you look at the definition, it is one mole of the solid formed from the opposite charge gaseous ions here. Okay. Okay. So one mole of is stress on the ionic crystal lattice form, therefore the product form must be one mole in solid state, while the reactant is in gaseous cation and anion in here. Okay. So the one mole is stressed at the solid. So in the gaseous anion, no matter how many mole you use, doesn't really matter in here. Okay. So in here, you can see that enthalpy change is exothermic reaction because we have electrostatic attraction forces that is formed between the oppositely charged ions in here. So that is why the process forms exothermic in here. Okay, so lattice energy is depending on two factors. One is the interionic charge in between the two oppositely charged ion, and another one is the interionic radius. So as you can see from the interrelationship in here, lattice energy is directly proportional to the charge between the two ions, yet inversely proportional to the interionic radii. Okay, so how are we going to describe this phenomenon? So we are going to say that so greater the charge of both opposite charge ions, stronger the electrostatic attraction forces between the giant ionic lattice, therefore greater the lattice energy. In terms of interionic radii, so shorter the interionic radii distance between the ion, closer both ions are attracted, so greater the lattice energy in here. So in short, if we want to have a compound with high lattice energy, you must have a high charge and small interionic radii. All right. So this is what are the factors that influence the lattice energy. Then we are going to have a look at the next one, which is the enthalpy change of hydration. So the definition of enthalpy change of hydration can be defined as the energy released when one mole of gaseous ion is dissolved in excess water to form aqueous ion solutions. Okay, under standard condition. So if positive gas, it can be positive, it can be negative. So if it is hydrogen gas from hydrogen aqueous solution, so its reaction is exothermic. If Na plus gas give Na plus aqueous, so the enthalpy change of hydration is also exothermic. So Mg2 plus give Mg2 plus gas, enthalpy change of hydration is this one. So in hydration, the intermolecular forces in here we are talking about is the ion dipole. This is an ion dipole attraction where the partial negative charge of the hydrogen ion oxide the oxygen atoms inside the water attracting the positively charged ion. So hydration can also see from the angle separately for the anion. Okay, so for the anion, okay, if you, let's say for example, we have F minus give F minus aqueous. Okay, and then if I minus gas give I minus aqueous. O2 minus gas give O2 minus aqueous. So all of them are exothermic, as you can see here. So similar to the cation or the anion, it is also ion dipole attraction, okay, where the partial positive charge of the uh, hydrogen ions will attract with the negatively charged ions in here, okay. So why is all this process is exothermic? Because the ion dipole attraction is very strong and therefore needs a lot of heat when attracted here. Okay, so what are the factors that influence the enthalpy change of the hydration? We say the enthalpy change of hydration is directly proportional to the charge, yet inversely proportional to the ionic radius. So in terms of the uh, hydration, okay, unlike lattice energy, for hydration, they are considered separately, yeah. So greater the charge of the ion, greater the polarity of the ions with the water molecule, therefore the more exothermic of the hydration, okay. In terms of ionic radius, smaller the ionic radius of both cation and anion, greater the polarization of water by the ions, and the more exothermic the hydration is. So, in short, we say that if you want to have a high enthalpy change of hydration, you must have a high charge and small ionic radius. But unlike lattice energy you consider both together, whereas in the hydration, they are separate. Okay. All right, finally, we are going to have a look at the third enthalpy change, which is the enthalpy change of solution. So standard enthalpy change of solution is the energy changes when 1 mole of solute is dissolved in the excess water to form an infinite dilute aqueous solution. The standard conditions. So here are a few examples. If it is ionic, no need to write water. So NaCl solid give Na plus aqueous plus Cl minus aqueous. If MgF2 solid, give Mg2 plus aqueous plus 2F minus aqueous. If silver bromide solid, give silver bromide silver ion aqueous and bromide ion aqueous. Yeah, okay. So and then same things can apply for the covalent compound, but in our lesson we are going to focus more on the ionic compounds in here. Okay. Okay. So it can be endo, it can be exo. If you look carefully, some of them are positive, some of them are negative here. Right. Okay. So technically, if you want to, how can the enthalpy change of solution help us to understand about the solubility of the substance? So when we have solute dissolved inside solvent, so there is two possibilities. So if the enthalpy change of the solution is endothermic, okay, so we describe it as the solute is sparingly soluble in water. If the enthalpy change of solution is endothermic, so we describe that the solute is sparingly soluble in water. So you're going to see precipitate throughout here. So there is an exception for this. So this exception applies to sodium, potassium, and ammonium ions. Whereas for the if enthalpy change of the solution is exothermic, so the solute is usually soluble in water to form aqueous ion solution. So you can see you form a homogeneous solution in between the solute and the solvents in here. So how are we going to relate between the enthalpy change of the solution with the enthalpy change of hydration and lattice energy that we learned earlier? Okay, so let's have a look at their relationship. So we learned that enthalpy change of the lattice energy has the equation m plus gas plus x minus gas give mx solid. So this process is exothermic. For the enthalpy change of hydration, so you have m plus gas plus x minus gas give m plus aqueous plus x minus aqueous. So this process is also exothermic. So if you want to get the enthalpy change of solution, basically enthalpy change of solution is mx solid give m plus aqueous plus x minus aqueous. Now, how are we going to relate in between the lattice energy and also hydration in order to get enthalpy change of the solutions in here? So if you look carefully in here, technically you just reverse the lattice energy, right? You just switch the position of lattice energy. So that is why we reverse this lattice energy. So when you reverse the lattice energy, okay, so you become mx solid give m plus gas plus x minus gas. So you have negative of the lattice energy. So this one, okay. Then for the hydration, so you have the enthalpy change of hydration is m plus gas plus x minus gas. So can you now start to see their relationship in here? So you cancel the opposite side with the similar species. So x minus cancel with x minus. So at the end, what do you have? So at the end, you have enthalpy change of the solutions in here. So mx solid, okay, is m plus aqueous plus x minus aqueous. So therefore, as a conclusion, we can say that enthalpy change of the solution is equals to enthalpy change of the hydration minus lattice energy. Enthalpy change of solution is equal to enthalpy change of hydration minus lattice energy in here. Okay. Now, bear in mind that both of these processes are exothermic. Okay. Both of these processes are exothermic. If mathematically you want to imagine, so if we want, usually if we want to say that, if you want the enthalpy change of the solution to be negative, then if you want the enthalpy change of the solution to be negative, let's say, you will say that your hydration must be smaller than your lattice energy, isn't it? And conversely, if you want your enthalpy change of the solution to be greater, then your hydration must be greater than the lattice energy, isn't it? Now, don't forget, because both processes are exothermic in here. Okay, so if you want your enthalpy change of the solution to be exothermic, okay, so if you want the enthalpy change of solution to exothermic, so your hydration must be greater than the lattice energy. So you have more negative, okay, plus with less negative. So your answer will still remain as negative. And conversely, if you want your enthalpy change of solution to be endothermic, so your hydration must be smaller than your lattice energy. Because when you have more negative, that means you'll be more positive because minus minus will eventually become plus, isn't it? When you plus up or when you sum up with the less negative of the hydration, so overall you get positive here. I hope that you see the relationship, yeah? Okay, so how are we going to imagine the relationship between the lattice energy and the hydration that cause to the solutions in here? So now let's have a look at this diagram in here. In lattice energy, we are going to talk about the ionic bonding between the oppositely charged ions in here. Okay, so this one we measure using lattice energy, right? And then for the hydrations, okay, you are talking about how the Cl minus attracted to the hydrogen, okay, or how the negative, how does the positive charge will attract to the partial negative of the hydrogens in here. So just now we say that if you want your enthalpy change of the solution to be exothermic, that means you want your salt to be soluble in water. So you say that enthalpy change of the hydration must be greater than the lattice energy. That means the attraction in between the water and also the ion must be stronger. Okay, it must be stronger than the lattice energy. So if the lattice energy is weaker, so it is separate easier. So do you see the relationship here? And conversely, if you want your enthalpy change of solution to be exothermic, okay, so which will make the salt become sparingly soluble. The term sparingly soluble in here means that not that soluble lah, okay? So your lattice energy must be greater than your enthalpy change of the hydration. So technically, if your intermolecular forces is stronger, okay, if your electrostatic attraction forces is strong lah, even the water attracted to it, it is not strongly attracted lah. So when it is not strongly attracted, so it will remain as the strong intermolecular forces. So that is why you see as a precipitate. Does not dissolve inside water in here. So can you see the relationship in between what happened if the enthalpy change of solution is exothermic and the enthalpy change of solution is endothermic? Why is it soluble? Why we say that it is soluble and why we say that it is sparingly soluble? Okay, so I hope that this diagram can help you to understand better. Okay, so I summarize the table for you in order for your conveniences. Okay, so we say that if the enthalpy change of solution is exothermic, is when your enthalpy change of hydration is greater than for enthalpy change of solution to be endothermic. Okay, so you say that lattice energy is greater than the hydration. Okay, so your enthalpy change is positive. So they will cause the salt to be sparingly soluble in water. So this is due to high lattice energy of the salt cause the electrostatic attraction forces between the cation and ion to be strong, therefore hard to separate in water. And conversely, if you have the enthalpy change of the solution is exothermic, is when your hydration is greater than the lattice energy, therefore it has a negative value. So this will cause the solute to be soluble in water. Okay, so this is due to when you have a high hydration energy indicates that ions are strongly attracted to water. So therefore, while low lattice energy means that the attraction forces between the cation and the anion are not strong, that hence makes them easily dissolve inside water here. Okay, so in terms of the energy level diagram, so this is the energy level diagram between exothermic and endothermic, but this one will stress more in the coming semester 2. So I'm not sure whether semester 1 they will stress on the application of this diagram. Okay, so I will just leave it because you haven't learned endo exo. We are going to stress more in sem 2 later. All right. Okay, so now why do we have to go through all this first before we're explaining the solubility of the group 2 sulfate? This is due to, we are going to use these three factors to explain the solubility of the group 2 sulfates in here. Okay, so generally, when going down to the group 2 sulfates, okay, so we are going to say that solubility of the group 2 sulfate decrease down to the group, okay, where you are in here, you shall see that beryllium sulfate and magnesium sulfate are soluble in water, whereas calcium sulfate, strontium sulfate, and barium sulfate are sparingly soluble in water. So all these can be explained from the angle of enthalpy change of the solution in water, where we are going to relate through hydration and also lattice energy in here. Are you ready? Okay. So enthalpy change of the solution can be explained from using lattice energy and enthalpy change hydration. So here are the very important key points. Let's have a look together. So we say that solubility of group 2 sulfate decrease going down to the group 2, right? So where the enthalpy change of solution becoming from less negative to more positive as going down to group 2 sulfate. So using the relationship, enthalpy change of solution is equals to hydration minus lattice energy. So as both of the lattice energy and enthalpy change of the hydration is proportional to the charge and also ionic radius of ion. Hence, when going down group 2 sulfate, ionic radius increase. Both of these energy decrease as the ionic radius of the group 2 ion increase. Okay. Okay, so when both hydration and the lattice energy decrease, so as we already tried to describe, so if you look at the large sulfate ions in here, okay, so this is the distance between the sulfate, which is actually the same. Now, if you look carefully here, because sulfate ions by itself is already very large, so no matter which one you put next to it, you put beryllium next to it, you put magnesium next to it, you put calcium next to it, or you put strontium next to it, or you put barium next to it. So their interionic radius is not that much of a difference in here. Okay, compared to when you put as a hydrations in here. So hydrations are measured separately. So if there is no sulfate ion, you can see that the difference of the ions is very significant, isn't it? So that is why we say that the decrease in the hydration is less, the increase in the lattice energy, sorry, the decrease in the lattice energy is less significant compared to the decrease in the enthalpy change of the hydration, okay, due to the large sulfate ion size, okay. So as a result, the increase of the R plus R minus is very small and cause the lattice energy changes become less significant when going down to the group 2, okay. Whereas in the hydration, it depends on both cation and anion. So since the hydration of the anion is constant, so the hydrations is depend mostly of the size of the metal ion. So that is why it causes the enthalpy change of hydration to be much less exothermic lah, right? So since hydration is equals to enthalpy change of solution is equals to hydration minus lattice energy, therefore the value changes from negative to positive. So for beryllium and magnesium sulfate, they are soluble in water. Since the enthalpy change of solution are exothermic, plus calcium, strontium, and barium are sparingly soluble in water, since the enthalpy change of the solution is endothermic in here. Okay. Okay. So from this graph, I hope that you can see easily that this is the decrease in the rate of hydration, and this is the decrease in the lattice energy. Okay, so the borderline lies in here. Okay, so this is the borderline that separates between the two of these. Okay, so as you can see from here, okay, since the so if you look carefully, in between the hydration and also for beryllium sulfate and magnesium sulfate, since the hydration is greater than the lattice energy, so you make the solution to be negative. Therefore, the salt is soluble in water. Okay. Conversely, for the calcium, strontium, and barium, so the lattice energy is greater than the enthalpy change of the hydration. Okay. So this will make the enthalpy change of the solution to be endothermic. So they are sparingly soluble in the water. Okay. Okay. All right. So with that, that is all for our second part of the videos in here. So oh, never mind. We continue a little bit more because nothing much already. Okay, so we continue a little bit, we finish it, and then that's it. And finally, we go to the application of the group 2 compounds. So we are going to state the use of the group 2 compounds in here. Okay, so generally, beryllium is unreactive on air due to the passivating layers. So this will make the beryllium to be very resistant to corrosions. Okay, so this heatedness combined that it is one of the lightest metal result in used to alloy in making precision instrument, aircraft, and also missile. However, beryllium oxide is very toxic, so that is why it has very limited usage in here. All right. So we are not going to look a lot inside the beryllium. So we are going to focus on next magnesium. So most of the application of the magnesium are based on the light alloy. Okay, especially with the aluminium. that is widely used in the construction where weight is an issue in here. So magnesium aluminium alloy was previously used in the body of the airplane. So some of the uses of magnesium are based on the fact that it burns in air with an intense flame. So it is used in fireworks and also flare. Okay. So various application of magnesium compound, including milk of magnesia, which contain magnesium hydroxide, is used to treat indigestion. Okay, and then the Epsom salt, which is mainly made of magnesium sulfate, which is used for constipation. Okay, which is used for constipation. Then magnesium oxide is used in the refractory lining for the furnace and also casing of the high voltage electrical cables here. Okay. Okay, then we have calcium. So the compound of the calcium are much useful than the calcium itself. So calcium oxide, also known as lime or quicklime, is used as the major component of the mortar and cement. It is also used in the steel making and paper making. So calcium sulfate dihydrated is used in building materials such as the plasterboard, okay? And also anhydrous calcium sulfate is used as a drying agent here. So calcium sulfate is also used as the casting for the broken bones, okay, which is also known as the plaster of Paris, as you can see from the diagram here. So agriculturally, calcium carbonate together with some calcium oxide or magnesium oxide is often added to soil to increase the pH of the soil, which is to reduce the acidity of the soils in here, okay? Okay, and finally for strontium, it does not have many usage. It is used in the pyrotechnic phosphor and in glasses. Okay, and finally for barium, so it has a large advantage due to the large barium ion. It is very effective in absorbing X-ray, so it is used as a barium meal, which is used to investigate the intestinal tract in here. Okay, so that is why it is suitable to be used is the barium, and then the barium sulfate is also barium carbonate is used in the glass making and also used as a rat poison. Okay. Okay, so I guess with that we finish the chapter 5, and that is all for our video for chapter 5. We are going to continue on with the chapter 6 in our next video. Okay, so hope you have a great day and see you all